My name is Professor Anchi and my train number is S71181. This is my topic. For the introduction, the definition of nanomaterial is defined as material with dimensions that fall between 1 and 100 nanometers. They exhibit unique magnetic, electrical, optical, mechanical, and catalytic properties that distinguish them from bulk materials. They offer exceptionally high surface area due to their nanoscale structure. There are many applications that nanomaterials can utilize in, which is scratch-resistant paint and surface coating, electronics and energy storage device, cosmetic and environmental cleanup solution, and sport equipment and sensors. For the problem statement, there is lack of comprehensive research on how different synthesis methods affect key properties of zinc oxide nanostructures. Most studies focus on individual techniques without comparative analysis, limiting understanding of factors. There are three objectives. Firstly, to synthesize zinc oxide nanoparticles using the solid state, sol-gel, and combustion method. Secondly, to characterize zinc oxide nanoparticles using thermogravimetric analysis, X-ray diffraction, scanning electron microscopy, and ultraviolet visible spectroscopy. Thirdly, to study the effect of synthesis method on the band gap energies and antibacterial activities of zinc oxide nanoparticles. Zinc oxide is a versatile nanomaterial with a hexagonal oxide structure. It is known for its exceptional properties and has diverse applications across several fields. It is used in sensors, antimicrobial agents, optoelectronics, water purification, catalysis, energy storage, and piezoelectric devices. Its wide bandgap, high acetone binding energy, chemical stability, and biocompatibility make it suitable for advanced technology. There are many methods for the synthesis of zinc oxide nanoparticles, which include hydrothermal and sol-gel methods, green synthesis, cold precipitation, and combustion methods. Application of zinc oxide nanoparticles include in agriculture application. Its low toxicity and thermal stability make zinc nanoparticles safe for agriculture. Secondly, sensing technology is also one of the applications of zinc oxide nanoparticles. Thirdly, zinc oxide nanoparticles effectively decompose toxic substances including organophosphate and nitroaromatic compounds which pose health risks such as cancer and skin disorders. The definition of bandgap represents the energy difference between a material valence and conduction band. It is essential for electrical characteristics. There are three types of material based on bandgap, which is insulator with wide bandgap and low conductivity, semiconductor with moderate bandgap and control electron movement for electronic application, conductor with small or no bandgap and high conductivity. Engineering the bandgap through doping or composition changes is vital for creating material with target properties such as efficient solar cell or LEDs. For antibacterial studies, various techniques are employed to assess the antibacterial properties of zinc oxide nanoparticles. MIC testing involves sequential dilution of bacterial culture with the antibacterial agent, observing turbidity after a 24 hours incubation period at 37 degrees Celsius to determine the MIC. For the MBC testing, the culture is placed on agar medium to assess the impact of nanoparticles on bacterial growth. The chemical used for the experiment is zinc acetate dihydrate, zinc nitrate hexahydrate, triethanoamine, ultra-pure deionized water, ethanol, tartaric acid, and sodium hydroxide. The apparatus that used is beaker 100 ml, beaker 1000 ml, measuring cylinder, dropper, complex glass rod, agar mortar and pestle, magnetic stirrer, and crucible. In solid-state method, zinc acetate dihydrate will be homogeneously green and heat at a temperature of 600 degrees Celsius for a duration of 5 hours. The sol-gel method starts with zinc acetate dihydrate, which is dissolved in absolute ethanol and stirred for 30 minutes. The target acid or sodium hydroxide is added to adjust the pH to 6 and 7, forming a thick gel. The mixture is then heated to 100 degrees Celsius to create a white precursor, followed by calcinate for 600 degrees Celsius for 5 hours. In the combustion method, zinc nitrate hexahydrate is dissolved in ultra-pure deionized water with triethanol amine as fuel. The mixture is heated to 250 degrees Celsius until ignition occurs, leading to combustion. The resulting precursor materials are then ground into a fine powder using an agate mortar. Characterization of zinc oxide nanoparticles will be evaluated by using this instrument and analysis, which is thermogravimetry analysis (TGA), X-ray diffraction (SRD), scanning electron microscopy (SEM), and UV-based NIR spectroscopy. This is the expected result. This study focused on synthesizing pure single-phase zinc oxide nanoparticles. There are three synthesis techniques will be employed, which is solid-state, sol-gel, and self-propagating methods. The synthesized zinc oxide nanoparticles will be characterized using advanced techniques, include thermogravimetry analysis (TGA), X-ray diffraction (SRD), scanning electron microscopy (SEM), and UV visible spectroscopy (UV-based). Antibacterial properties will be evaluated using the diffusion method or mirror Hinton agar. Two types of bacteria will be tested for antibacterial activity. The goal of this research is to enhance zinc oxide nanoparticle synthesis, truly characterize their properties, and optimize band gap energies. Particular emphasis will be placed on their antibacterial potential for targeted application. That's all for the video. Thank you for watching.